Good afternoon, everyone. Thank you for joining us. My name is Janie Montblanc, and I'm with the Great Basin Fire Science Exchange, and with me is John Tull, Acting Sagebrush Ecosystem Coordinator with the U.S. Geological Survey Land Management Research Program, and Corey Gooker, Great Basin Fire Science Exchange Co-Coordinator. We'd like to welcome you to the fourth webinar in our Sagebrush Ecosystem Restoration and Fire Science series on the topic of vegetation and treatment monitoring, presented by USGS researchers. John Toll will be our host today, but before I hand the webinar over to him, I'll go over some webinar details. We're using Zoom Meeting as our platform with attendees' mics and cameras off. We'll take a couple of questions after each presentation and address additional questions at the end, time permitting. Please type your questions in the chat and John will field them to the presenters. Any questions we don't get to, we'll follow up with the speakers afterward and provide responses along with the video recording. And with that, I'll hand it over to John.
Thank you, Janae. Appreciate that. So this webinar series has been an ongoing collaboration primarily with the Bureau of Land Management, but also Fish and Wildlife Service and some other partners. Our goal in the SURF, Sagebrush Ecosystem and Rangeland Fire program, is to provide meaningful and actionable science for our partners. And these webinars provide an important tech transfer opportunity for our researchers and the managers for which we produce this science. So I thank you all for being here, and we appreciate it. As Janae mentioned, this is the fourth of a 5-part series. Our last one will be tomorrow. And I'll just say it again. If you have questions for our speakers, please put those in the chat during their presentations, and we'll get to those. We'll also field a few in between talks. We do have a shorter lineup today, so I think also at the end of this, what we'll do is we'll open it up for a panel format where our presenters can field additional questions at that time. So with that, I will go ahead and move into our program and introduce Michelle Jeffries. And she's going to be talking about Rangeland Monitoring Program, tech transfer tools for NORMP and ROAM monitoring, her ROAM monitoring project. Take it away. I see you, Michelle.
All right, let me get my screen share straightened out.
I hear you.
Okay.
And I see me. There we go. Now I see your slides.
Okay, good.
Take it away.
All right, so my name is Michelle Jeffries. I'm a biologist with the Forest and Rangeland Ecosystem Science Center in Boise, Idaho. And I'm actually going to be giving two pretty disjunct talks that are along the same theme. So these are the title slides for each, and there's only going to be one pause at the end for questions. Okay, so the first half of this, I'm going to be talking about the Oregon Rangeland Monitoring Program, or as we delightfully call it, ORMP. And this is a really collaborative project between many different levels of partnership. So primarily it's between the USGS and the Fish and Wildlife Service, but also very importantly, all the way down to the private landowners all across Oregon. So the ORMP program started around 2020 when there was a lot of funding provided for some large-scale restoration projects across land ownerships. And this is primarily in Eastern Oregon, and it was funded for habitat restoration primarily for sage grouse. And around 2021, 2022, they reached out to us asking for help with their reporting and monitoring. And so that's where we came into the program to help design their monitoring and reporting. So when we think about monitoring, our group likes to think of this really complicated teeter-totter because there's a lot of trade-offs when you're thinking about designing and implementing a monitoring program. And so there's some pretty key trade-offs that I'm going to talk through today and how we navigated and how we still are navigating this, tricky teeter-totter of trade-offs. So first, we're going to talk about how we defined our monitoring purpose and questions. And so we held an advisory group where we came together as partners and we started to outline what sort of questions that they were hoping to get answers to. And we binned these into these main groups from people like people who are funding the projects, all the way into scientists like myself that really like to work with detailed and complex data. And we further grouped these into 3 main tiers. So this top tier that I've highlighted here, this is going to be more of the general outcomes of ecosystem condition. And then this tier 2, this middle portion, this is more for the practitioners. So what happened in these treatments. And then this tier 3 approach gets into more of the detail and the why of these different outcomes. So I'm going to talk through these tiers very briefly, and this is sort of how we think about it as a funnel of kind of more general information funneling into more specific information. So tier 1 is where we think about overall ecosystem function. And we ask questions about ecosystem function by thinking about things like the ecological state of that area. How is this area trending? Is this site resilient? And what's the general condition of this plot? And we're categorizing things, or we're answering these different questions using, ratios of different functional groups, as well as classifying these different areas into a specific ecostate. And this ecostate approach has been very successful in Oregon. And we use this decision tree to help walk you through lumping this area into these general categories. So we don't need to focus on all the details here, but we're essentially trying to get people to think in states. Is this a state A, which is a good condition shrubland? Like, does the landscape look like this? Or is this something maybe like a state D, where it looks like this? And the Oregon folks have had some great success in communicating information like this. Everyone can understand this ecological state sort of question, and you can drive around the landscape and think about it with these kind of states in mind, and it really communicates well across all partnerships. For this tier 2 information, we're getting a little bit more specific. So this is where we're starting to really dig into the cover of specific things. So we're starting to look at, did our treatment change, or how did it affect the cover of some specific groups or species? And there's several different types of treatments that we're monitoring. So there might be a different grouping that we're interested in for different questions. So some herbicides are targeting, specific species, and so we can evaluate the cover of those specific species or at the functional group level. And we are doing this by classifying cover in 2 ways. So at all plots, we do visual estimates of cover with cover guides, and then at a subset of plots, we also do line point intercept. And this tier 3 information gets into more of the nitty-gritty of thinking about, okay, here's the pattern of the data. How does that compare to ecologically relevant control areas? And why do we see some of the trends that we're seeing? All right, so once we figured out all of our goals and questions, the group came up with a wish list for their monitoring design. And so this was the wish list that came out of that group. So they wanted pre and post treatment. They wanted to include control plots. They want to frequently monitor them, at least for the duration of the treatment effect. This adaptive design concept, a lot of these treatments are implemented on top of each other, where they're doing repeat treatments year over year. So this design accounts for that. And for data certainty, they wanted informed data, but it didn't necessarily need to meet the rigor of like a scientific journal, for example. And, from this, for inference for individual treatments, we decided on about 20 plots per treatment and control for those treatments. And we have the ability to pool data across the whole landscape. So everyone is collecting the same sort of information. So we can pull data across larger landscapes, including control data as well. And then at a treatment scale, we helped stratify these plots by ecologically relevant conditions. So for both the treatment area and a control area around it, we stratified their sampling design by elevation and heat load. And so the control areas were matched by the areas that are found within the treated area. And then we randomly stratified within these groupings to ensure we're sampling across this potential ecological gradient on all of the treatments. Then the scale of this work is pretty large. So some of these treatments can be as small as about 5 acres, and some of them getting close to about 20,000 acres. And they're found in several counties all across Oregon that are implementing this work. And some of these areas are just very complicated and stacked treatments. So pretty large scale work going across most of Oregon. All right, so we're helping this group with their capacity in several ways. So we are helping to remove barriers of data collection by helping them with this very accessible monitoring design and streamlined data collection. And all of the data that we're collecting is a shared survey form, and it's controlled by group defaults, so it auto-populates a lot of information for them, and it all comes back to the same backend database. So even if you're working for this county or that county, you may have a slightly different front end, but the backend data is all shared and all accessible to the right folks. And lastly, this data is also being rolled up in a couple different ways. So the treatment data, when allowed, are being included in the Land Treatment Digital Library, which is a digital repository of treatment data, which then means it's going to be accessible in the Land Treatment Exploration tool to learn from when planning future treatments. We're also designing some results dashboards for the project partners, and I will show a couple screenshots of those briefly. So during the field season, we're also helping out with their data quality. So this is what we call our in-season dashboard that is live linked to the survey data as it gets submitted. So this is a way that we can keep on top of quality control while the data are being collected. So this top part includes filters that you can narrow it down to your specific group. This part on the left gives you some summary information so you can make sure the number of forms you have submitted matches the number of plots. Make sure those numbers match. And this right side is where we show all of our charts, and this particular view is showing you the unknown species. So if you've got a field crew out, someone at the office can help identify the unknown species as they come in, and they can be automatically updated in the survey data as they are identified. And then after all the data are collected, QC'd, then we have these dashboards for data summarization. So this is just a screen capture of one of those views. So all of our project partners came together and they created a mock-up of these are the types of things I want to be able to see and do with these data. And from that mock-up, I've created some dashboards. So this is showing one of the dashboards. This is the tier 1 view, which is looking at general ecostate condition and ratio of bad things to good things, and looking at this particular treatment through time. And it's all interactive. And so you can hover over data, you can highlight things, and really get a good sense of the data, and you can change your filters and really dig into different questions. We also have dashboards for data reporting. So these are a little bit less interactive. They're more meant to create like PDFs for each treatment. So you have a standardized report on that treatment and the data behind it. And it includes information from tier 1 all the way down to tier 3. And here are the two main contacts. So Jackie Couples is the Fish and Wildlife Coordinator for this project, and Robert Arkle is the lead here at USGS. And this website URL is the ORMP website where you can get more information, and you can scan this QR code to go there. So that's the end of the ORMP portion of this talk. So I'm going to shift gears a little bit over, and now we're going to talk about similar but different talk, more about improving the rationale for how we choose monitoring methods for rangelands. And so some of the methods that are used in ORMP are the methods that we're evaluating in ROAM. So there is a little bit of crossover just with the methods. Okay, so what is this project? So we've called it ROAM. We like our acronyms. And that has come to describe rapid and other assessment and monitoring methods. And essentially, we measure everything so that you don't have to. So we extensively are comparing traditional monitoring methods with some more rapid protocols to see how well different methods perform under different conditions and for different metrics. So the goals of ROAM are to identify, test, and verify rapid methods to help us understand restoration success, to convey the importance of standardization, repeatability, data management, and training, and very importantly, to complement the BLM AIM strategy. So they're project partners on this and have been involved from the beginning. Okay, so the approach that we take has been to evaluate many methods at the same plot. And this is not the first type of study that has done, method comparisons. However, the novel thing is that we're doing so many methods at the same plot, including some that hadn't really been evaluated in rangelands before. So we do things like downward facing photos and several different point intercept methods. Stick point intercept, for example, is what was used for land PKS, or step point intercept has been used forever, like boot notch intercept. And we're also recording height and gap with all these different point intercept methods. We had several different density methods. We were doing point quarter for density and cover. And we had several different classification estimates, including visual estimates of cover, as well as those ecostate classifications. And then at a subset of these plots, we did have drone imagery flown on top. So our crew spent about a 10 to 12 hour day at each one of these plots, and they recorded all of this very detailed information. And we recorded their effort with start and stop times and all of the different metrics across these different gradients, all the way from a really invaded site up into getting into some more high elevation conifer. I'm not going to spend a lot of time on this slide, but here's a quick graphic of what our plots looked like. So all of these methods were stacked on top of each other at this same location. And we took a lot of care to make sure that we weren't trampling specific aspects of the plot so that wasn't a problem. So we were able to collect 62 roam plots across Montana, Idaho, Oregon, and Nevada. And some of these plots were intact communities. Some of them were recent post-fire. Some of these burned a long time ago. Some of these were juniper woodlands. So we really went through an effort to sample across several different communities of information. And we got results in two ways, and I'm going to share a little bit about both portions of results. So this portion is where we surveyed the surveyors. So of our entire population of field data collectors that did this method, which is only 6, but we surveyed them all, we asked them how they thought about how versatile these different methods were across the communities, how efficient they were to collect, and how representative of the plot that they thought they were. And it was a really long survey. It's about 150 questions long. And here's an example question that we asked them. So how well does LPI characterize cover at the plot? And they give a rating, and you get like this little Uber kind of 4 out of 5 stars. And this chart takes a summary of a lot of those results and kind of plots them against each other. So I'm going to build this chart slowly. But across the x-axis here, we have some point intercept methods. We have line point intercept, step point intercept, or boot notch. We have grid point photos, which is downward facing photos, stick point, which is similar to land PKS. And then we have visual estimates of cover and point quarter, which is measuring the distance and size of things. And I'm going to build this plot with 3 colors, so versatility, how representative and efficient. And then on the y-axis, we have their ranking across the group, and a lower value is better. So the lower on the y-axis, the better. Okay, so here's what the crew thought about the versatility of cover methods. So they ranked line point intercept as the most versatile method. And for representative, you can see, a little bit of a difference between the blue and gray bars. And we now actually have a tie of how well the crew thought that LPI and ocular estimates did for how representative of the plot those methods were. And then lastly, we have the how they thought about on how efficient they were to collect. You can see the crew really did like point quarter for any of the metrics, but especially the efficiency and representation of the plot. But for efficiency, those ocular or visual estimates, no surprise to us, came out as being the most efficient to collect. So it's good to see that come out because that's what we expected. All right, so I do have a little bit of time to share some of the field data as well. So here's from the data itself, so looking at the actual time it took our crew to do these different things. Let's think about the efficiency. And for this chart, I've simplified it a little bit. So we're just looking at stick point intercept, which is like land peak AS, step point or boot notch, line point intercept, and visual estimates. And here's what that looked like with the survey data. So we can see the point intercept methods, took about an hour or more for that plot. And of those point intercept methods, line point intercept was actually maybe a little bit faster than those other methods. And that the visual estimates averaged about 8 minutes to complete that portion of the survey. All right, so how representative were these different methods? And I'm just going to look at native shrub cover today to make it nice and simple. And on this plot over here, I've got boot notch intercept or step point on the y-axis. And then on the bottom of both, we have line point intercept. And then on this y-axis, we have stick point intercept or land PKS. So when we compare step point intercept to line point intercept for this functional group as an example, we actually get a very strong agreement between those 2 point intercept methods. So we were able to get pretty similar cover metrics from both methods, and they're pretty tight to the one-to-one line. That was really good to see. When we look at line point intercept to stick point, we see a little bit weaker agreement. We see that stick point intercept might be underestimating cover of shrubs, which actually makes a lot of sense. Despite us trying to randomly drop a stick in a shrub, the tendency of that stick is still to fall out of the shrub. And so our crews actually noted that in our survey results, and it was nice to see it in the data in agreement as well. And this chart is a little busy, but I'm going to walk us through it. So we oversampled with line point intercept. So typically line point intercept has 3 spokes of data. So we collected 6 spoke LPI. So we doubled the amount of data we were collecting for line point intercept. And we compared the data, the cover estimates for native shrub cover in this example, from the 3 main spokes to the 3 additional or the secondary spokes. So that comparison on the X and Y axis are the blue circles. So this is the difference, the cover from the 3 versus the other 3. And then the orange circles are the primary 3 LPI spokes versus the visual estimate. So when someone was categorizing native shrub cover visually into a bin, that's how it compared to the primary spoke. And the main thing you get from this is that there's variability regardless of what method you're using, and we'll never actually know truth. But if we accept that the amount of variability of LPI, if you just rotate the spoke, if we accept this level of variability as okay, the visual estimate variability is actually very similar, and the correlations are very similar when you correlate the visual estimates to the primary spokes. So this might be some evidence to suggest that visual estimates might be pretty okay to use. So there's a lot more to untangle with all this data. We're still digging into a lot of the meat of this analysis, but essentially we're trying to provide guidance for the right method in the right place at the right time across these different ecosystem conditions, across the different metrics that you're trying to understand. If your goal is to monitor sagebrush seedlings, for example, like what method might make the most sense, and provide guidance out to the community about that. So I just want to say thank you. And here are the two QR codes for the project pages for these two projects. So here's the Rome project page, and here's the ORMP project page. Thank you.
Thanks, Michelle. Those are great projects and great talks that you gave on them. I appreciate that. There's one question from George in the chat right now, and he asked if there's any elements of randomization in any of the methods you covered. I would think perhaps maybe like your lines, did they all go according to cardinal directions, or were they randomly selected? That might be one element of that.
If this is in relation to Rome, our plots were always the same and the same directions. So our plots for Rome always look like this. Every single plot looked like this. For the ORMP project, all of those plots are randomly stratified on the landscape, if that's maybe the question you're getting at.
Great. And then I'm just curious, so you may have covered it and I may have missed it, but how long does it take to do the stick point versus a 3-spoke LPI?
It's surprisingly similar. And maybe just a little bit slower because you gotta like move the stick manually. Because like I said, they would try to drop the stick to not avoid shrubs, and they'd have to like place it where it would have fallen. So there's some logistical additions that you get from stick point, but here's the data on the time.
Great. Well, I think, as I said at the end, we'll have time to come back if there's other questions. There might be some that show up in the chat. I encourage people to put additional questions there for Michelle. She can be working on answers for those, and we can save some for a little bit of a panel format at the end. So thank you again. And with that, we'll go ahead and move on to our next speaker. It was Chad Kluender. And Chad is going to be speaking about adapting digital geotech to work at the scale of management. And here he is to explain exactly what that means. Take it away, Chad.
Thanks, John. Yeah, my name's Chad Kluender. I work closely with Matt in the fires group at the Snake River Field Station here in Boise. Thanks for having me. So yeah, my talk is about adapting rapidly advancing digital geotech to the scale of management. And geotech can mean a lot of things, but I'm going to focus on decision-ready spatial products because that is where imagery, field data, and prediction models become something managers can see and act upon. And I think sagebrush steppe landscapes are a good setting to discuss this because many of our hardest problems are inherently spatial. Got annual grass invasion, fire risk, fuel continuity, treatment placement, and treatment outcomes. And these questions depend on where vegetation is and how that pattern is changing. And now it's clear that we can make faster, higher resolution mapping products, but the harder question is whether they are accurate, current, locally validated, and interpretable enough to support decisions on the ground. So what's possible? So we're moving from coarse generalized vegetation layers towards decision-specific management products. So at the finest scales, UAV imagery can now support centimeter resolution predictions, visualizing a variety of landscape responses. These products are helping guide precision restoration and accurate inference about treatment effects. At broader scales, near daily 3-meter satellite imagery can now support accurate vegetation mapping when you correctly time the phenology, weather pattern, and species signal of a unique site. So I think the main point is that our geospatial toolbox is getting much larger and more sophisticated, and it now allows for the creation of unique and better suited spatial products for the varying problems at hand. So a bad map can put real costs onto a manager. So if a poorly validated product overestimates annual grass cover, then you could have seed, chemical, contractor capacity going to the wrong place or causing actual ecological harm. And if a product underestimates invasion, managers may miss the optimal and efficient treatment window, or if a map is just wrongly shifted in space, a contractor, even now autonomous spray systems may treat the wrong area. And the same issues show up in field sampling. If we try to create a spatial product that exceeds what the input monitoring data can support, then we may wrongly infer effects when in reality, the input data is just too coarse, misaligned, or collected at the wrong scale. So the overall goal is avoiding the wrong acres, the wrong timing, the wrong guidance, and the wrong inferences. So I want to say that public products like RAP and RCMAP are extremely valuable for broad context, regional screening, and time series comparisons. I think they now really help us dial in where on the landscape we should be looking more closely. Where I get cautious, though, is when I'm seeing managers using them as absolute value layers for treatment placement and post-treatment inference. So I like to use and adapt these products for screening, but not use them for final answers for informing treatment polygons or prescriptions or assessing treatment outcomes. I think the main question we should always ask is what level of error or spatial uncertainty could change a decision on the ground, and what would be the cost of that wrong decision? So one limitation of many standard field monitoring techniques and the spatial products derive from them is that they summarize vegetation composition without preserving its spatial arrangement. Plot and transect data can be useful, but they often reduce complex patterns to average cover. Say in one plot, annual grass may be a discrete patch. In another, the same amount may be intermixed with perennial bunch grasses. The cover values there are identical, but the treatment and monitoring implications are not. So useful geospatial products meant to inform precision restoration and monitoring requires field data that captures pattern, configuration, and neighborhood context, not just fractional vegetation cover alone. So the core framework is to match the spatial product to the management objective. So for regional vegetation screening, public products plus local field data correction may be enough. For treatment prioritization across an allotment or refuge, a higher resolution, locally adapted satellite model and properly timed and robust field data is more appropriate. For precision restoration, post-treatment patterning, really any fine scale pattern recognition, 10 or 30 meter products are not sufficient. In general, regional screening products should not be treated like a prioritization map, and that prioritization map should not be validated like a broad monitoring product. So the most important part of these modern geospatial workflows is still the field data. Models cannot rescue weak or misaligned labels or poor cover estimates. If training data are poorly located, spatially biased, or missing key landscape variability, the model may look sophisticated, but still learn the wrong thing. So we're now emphasizing repeatable field workflows using survey grade RTK and validation checkpoints among field data, imagery, and the final products that are produced. Relative alignment matters for training the model, but absolute alignment matters when people need to navigate back to the field and apply treatment in the right place. This is where targeted sampling design becomes important, especially on large landscapes. The goal is not just to spread plots across geographic space. The goal is to collect training and validation data across the conditions the model is asked to predict. So one way to do this is to reduce the predictor space into major environmental gradients and prioritize field locations that fill those gaps. The field data need to represent the whole landscape, that improves the model and the trust because the map was trained and checked with local data designed around the unique project area in question. So existing field data sets were not designed to inform these modern products. Line point intercept, ocular cover, and other methods are valuable for plot scale condition, trend, or composition monitoring, but that's very different from training a model on UAV imagery or validating a 3-meter cover model. Each product needs the right field truth, and that means matching the pixel scale, the vegetation phenology, and landscape environmental gradients. Or for a segmentation map, ensuring the labels preserve representative vegetation boundaries and monitoring checks that separate actual ecological change from model uncertainty or just timing. So I'm trying to build a workflow that can be summarized as timely, defensible, and repeatable. Timely means managers get a usable product inside their decision window. This is achievable by precisely targeting the right phenology for your objective, using daily imagery archives, and processing and delivering the spatial product sometimes in the same day the field data was collected. Defensible means the output is locally accurate, tied to contemporary field data, and transparent about uncertainty. And repeatable means that the field design, imagery selection, modeling approach, and validation are documented and transferable. So these workflows all revolve around needing to match the input imagery to the decision. This generally looks like obtaining high resolution, multispectral UAV images that act as your gold standard truth layer for labels and calibration. Then for larger landscapes, we can scale that with high frequency satellite imagery or task out commercial satellites for very high resolution sub-meter imagery. The input mapping stack will change with the question. Daily satellite data help when phenology or rapid change matters. Taskable imagery helps when the fine detail is needed, and UAVs help when we need the highest spatial detail possible. Again, we just need to think about building the product around the decision that's being made. So the other piece I want to emphasize is ecological supervision. Machine and deep learning models are getting increasingly good at separating spectral patterns, texture, shape, and context, and are now much easier to run and build. But a model doesn't know what is management relevant on the ground. It doesn't know if a vegetation class should be split or grouped or what threshold cover value matters in a certain scenario. In general, yeah, model can predict the pixels, but an ecologist should decide which predictions are meaningful and how to make spatial products useful. In general, the final product should be a set of interpretation-ready layers, including confidence surfaces, management polygons, validation points, metadata, and clear use limits. So to close here, I think we should just all be aware that digital geotech is advancing very rapidly in terms of satellite and UAV technology, modeling architecture and the ease of use of that, and computational power and efficiency. I think this creates major opportunity for rangeland management, fire management, and restoration. We are getting products cheaper, better, and faster, but the value really comes from matching the correct tool to the unique question. In summary, that means using local field data, adapting sampling methodology, sampling the landscape heterogeneity that matters with high precision, and choosing imagery whose resolution and timing match the objective. And so to close, I don't think every usable product needs UAV imagery or a heavy deep learning model, but when a decision is expensive, spatially specific, and ecologically consequential, the workflow should be built to the same standard as that decision. That's all I got. I know I kept this really high level, so happy to dig into the details or answer questions later.
Thank you, Chad.
Yeah.
Yeah, I think I had a question for you myself. You kind of touched on it at the end, and it was basically, can we scale a workflow like what you've described at reasonable costs. How much, if somebody's trying to make, say, um, a decision on a sub 10,000 acre landscape scale, um, are they going to be able to afford to do something as involved as what you've described?
Yeah, I think as time goes on, even in the next year, these satellite products at the sub-meter scale are going to become cheap enough and accessible enough to do a workflow at the 10,000 meter scale or 10,000 acre scale. Even now, it's not as expensive as people may think it is.
Mhm. And would that also rely on, it was a UAV component then to do the
Yeah,
calibration? Yeah,
yeah. So you'd fuse your UAV imagery and modeling architecture with your high resolution satellite data.
great. That's interesting stuff. And I think I've got a broader question I'll say for our panel when we rejoin in a little bit here. I don't see any questions in the chat at this point. Again, I encourage people to add your questions to the chat and we'll queue them up and our presenters can answer those for you also during the course of the webinar today. But with that, I'll go ahead and invite our last speaker who's Matthew Rigge, and he's going to talk about RCMAP vegetation trend summaries.
Yeah, thanks, John.
Matthew, I hear you.
Just wanted to show my face for a moment here. I'm on a oh, can you hear me?
I can hear you.
Hello?
Yep, I hear
Okay,
you.
good.
So yeah, go ahead and turn your video off if your bandwidth's limited. That's
Yep.
fine. We understand.
Yes, I apologize for that.
And in case you didn't hear, because I know you had to join late, we were going to keep people around for a few minutes after since we have a shorter session today
That's
for panel questions.
that's perfect. Can you
Great.
see all
All
right,
right.
John?
I can see everything. I'm going to hand it over to you. Thank you, Matt.
Okay. All right, thank you. All right, so today talking about RCMAP with a focus on temporal trends. So first of all, I need to thank my collaborators at AROS, the BLM, Wildlife, and AIM programs for funding, the USGS, WLCI, and NLI programs as well for support. So RCMAP, Rangeland Condition Monitoring Assessment and Projection, is really designed to capture gradual and abrupt changes in rangeland condition over the whole Landsat time series stretching back to 1985. And the whole idea there is that retrospective analysis of the effectiveness of previous management actions and disturbances help improve our decision making moving forward. And I really appreciated Chad's talk as well. I think it's really critical to highlight the importance of local field observations and other ancillary data sets like climate observations, etc., to augment any conclusions derived from our data or similar data. So RCMAP produces a set of 10 fractional components on an annual basis, leveraging AIM data, Landsat imagery, and machine learning. So we updated our products and released a new generation of data last month that extended the time series through 2025, added a bunch of new training data from AIM, some UAV data from Western South Dakota, collected by Aaron Johnston, in a particularly difficult to map sagebrush region. And we added several new high resolution training sites in the Great Plains. That's one of the unique elements of RCMAP relative to RAP is we leverage a lot of our custom high resolution predictions at 300 plus sites across the West using Worldview 2 or 3 high resolution imagery is a really unique aspect of RCMAP. We have enhanced our post-processing with some better statistical methods. And I mentioned this in my presentation yesterday, if you were there. We have integrated the exotic annual grass products into the RCMAP hierarchy. So those are a set of 8 fractional components produced on a weekly basis during the growing season as compared to the annual basis of the regular RCMAP products. So high level picture of what the components look like. I think typically follow the expected patterns. But again, the most interesting thing here is the temporal aspect. And I've got an animation here, hopefully it shows okay, of how all these components have changed between 85 and 2025. So some significant changes are, of course, in the tree cover component, increasing across a lot of the Great Plains, sagebrush declining in many regions as a result of fire, and bare ground declining as a result of invasion by cheatgrass, etc. So distilling all of that information on that animation into a single DLSEN slope per pixel. So I've got blue noting decreases in that component cover through time, and red is increases in that component through time. So some of the big patterns going on here: increase in herbaceous cover in a lot of the burned areas across the Great Plains and Great Basin, and many of those same places having increases in annuals. Tree cover increases in a lot of the Great Plains, I mentioned that before, and bare ground decreasing a lot across a lot of the northern Great Plains into like eastern Montana. That's related to a long-term increase in precip over the last several decades.
Matt, we just
Yeah.
got that slide. I just wanted to let you know, you may want to leave this slide up for a couple more seconds because it loaded really, it was delayed for us.
All right. My apologies. We're relying on a Wi-Fi hotspot here. So looking at those same patterns summarized by ecoregion, kind of an interesting way to really dial in on what are the big picture patterns going on across the landscape. Definitely noticing the patterns related to fire, with increases in herbaceous cover and decreases in shrub cover being related. Another kind of look at across the entire study area, which captures all of the western and central US. What are the big overall patterns in change? Of course, I'm preaching to the choir here with sagebrush trending downward, bare ground also trending downward overall. Sort of some conflicting geographic patterns there in the east versus the west. Tree cover increasing as well overall. And of course, unfortunately, the increase in annual herbaceous, which includes invasive annual grasses. So one thing we can do now, we have held a set of 6,000 aim points for independent validation. So these are mutual points held back by both RCMAP, RAP, and anyone else who wants to participate for validation activities. And we have enough N now per ecoregion, in many ecoregions at least, to get an idea of patterns of accuracy by how that varies spatially. So some general takeaways here are that the more common that component is in that ecoregion, the higher the accuracy tends to be. Also, the higher the cover in general, it tends to be more accurate. So an ecoregion that has a mean of like 20% sagebrush cover will have higher accuracy in sage than an ecoregion with a mean of 4% sage cover, as an example. So that was bias, this slide. So showing how far on average, we are above or below the mean of the field observations. And the next slide here is correlation by ecoregion. I am only showing ecoregions here that have an N of at least 10 aim points withheld in that ecoregion, which is a bit limiting, unfortunately. And still, even at this scale, there's a ton of internal variation within ecoregions, obviously. So results will vary even at this scale. Generally speaking, all of these sort of products suffer from regression to the mean. That is one of the key problems we face. So the models will tend to deflate high-end values and inflate low-end values. So that would show up as something that's really 100% bare ground in the map is maybe 90%, and something that's 0% tree cover might show up as 3 or 4% tree cover. That's an important caveat to be aware of. So looking at the accuracy of our products by version, I've got a summary here at those 6,600 withheld aim points, all the components. So we're looking across the V4 through V8 RCMAP releases. All of them are spaced about a year apart, and the accuracy keeps on going up and up because of more training data, better AI, better imagery compositing methodology, etc. So it's definitely cool to see that trend of increasing accuracy, especially in components like shrub and sage. We have really increased our accuracy even relative to 2 or 3 years ago. In terms of both correlation, the bar chart on the left, and in terms of reducing RMSE on the bar chart on the right. One other thing to note is that version 8 RCMAP, the one we released just last month, has more temporal variation than the V7 release from the prior year. That was one of my criticisms of our prior release, is some of the temporal changes were a bit muted. And I think that's still the case. And I think that will be the case for every geospatial product like RCMAP and RAP. Same thing as the regression to the mean in space, there is a regression to the mean in time as well. So by that I mean, if we have a disturbance come through, say a fire, the pre-fire shrub cover was 25%, the post-fire shrub cover is 0, you might see a change in the map of 25 to 5 through time. So that temporal change tends to be a bit muted relative to reality. What I'm showing here is just the V8 herbaceous component, as an example, has a more temporally dynamic profile compared to our previous version, and that results in a better correlation with precipitation, as an example. So looking ahead, we keep on chipping away at error in each version. We've been working together with RAP, Landfire, and others in the fractional component community of practice, helping users better access, analyze, and interpret data. So there's been a number of publications by that group, more in the works, and that engagement is becoming increasingly important as these data become more and more applied to decision making. That integration of EAG data into RCMAP will continue and be more refined in future years, and we plan on releasing a new version of RCMAP next spring that will extend the record through 2026. And lastly, we are working on a vegetation warning system to detect anomalous relationships between RCMAP components and weather. So for example, we would expect a positive correlation between herbaceous cover and precipitation through time. The system would detect when that relationship has deviated from the expected relationship or has become sort of more erratic through time. And that's all I have. Happy to take any questions.
Thank you, Matthew. That's great. I didn't see anything come into the chat, but I've got one for you. I really appreciate that you all do those accuracy over time comparisons to provide an honest accounting of sort of what's changed, and importantly, that we see a really good continuing trajectory of improvement. You mentioned chipping away at error, and I'm wondering, do you have any particular areas of improvement you see as having the highest potential for making RCMAP an even stronger platform than it already is?
Yes. So more training data, more training data. That's really what we need. There's no such thing as too much training data. These AI models are really data hungry, especially when you throw like 100 different predictor variables at the model. It just becomes the need for training data increases more. Hyperspectral data. So we've worked a lot with Landsat data that has 8 bands of information, done some experiments with emit hyperspectral data that has 285 bands, which is showed huge potential in terms of improving accuracy. In our little test, we reduced error by like 35% by incorporating hyperspectral data. There's some major limitations in those data as well, but I think in the new generation of Landsat data moving forward, there'll be more spectral information, and that will help improve models. Now, the rub on that, of course, is how do you do the past? We have more information to improve maps right now, but you're going to have temporal inconsistency anything you do now. So unless someone can invent a time machine and get hyperspectral data from the 80s, we might be out of luck. You might need to do sort of 2 parallel time series. RAP has sort of done that with their 10-meter data using HLS data from 16 onward, or 18 onward rather, and Landsat from 85 onward. So there's sort of a pros and cons of improving your data inputs in terms of the consistency through time.
Yeah, no, those are, I mean, that's at some point it's not a planned obsolescence or anything like that, but it's just the feature set's going to be too great to not take advantage of, and you can't go back. And we'll have to figure out how to reconcile those trends.
I mean,
Yeah.
the interesting thing is you add a new aim point from 2025 as an example in some area that didn't have data previously, that will impact predictions hundreds of miles away sometimes, and decades before that. Whatever the model has associated with that, it's interesting how a single new data point has trickle down effects through space and time.
I'm not sure if that inspires confidence or takes it away, but it's interesting point to note. Yeah. Well, thanks for
Yeah.
sharing about that work. I'm going to invite all of our speakers to come on camera if they have the bandwidth to do so. And I think we have at least a few questions sort of lined up, and Janae's got a couple she collected from the audience in advance, so we'll hand it over to her.
Great, thanks. Yeah, I believe this is probably a question for Michelle and or Stella, but what are some recommended monitoring protocols that are easy and informative for ranchers to adopt?
Sure, I can start. The ORMP program has adopted methods that they even have high school interns employing on private lands. And lots of other professionals as well are using these methods. So there's definitely a way to make a simple method meaningful if you have the proper training. So I gave an example of that ecostate classification. The ocular estimates of cover can be powerful as well and simple. I think that would be a good place to start with something like that. But I think it comes back to what kind of question is that person trying to answer to really define what makes the most sense.
Great, thanks. So if people wanted to look into that, they could contact you or that link I know you had on your last slide.
Yeah, I can
Okay.
put it in the chat too.
Okay, awesome. Thank you.
Yeah, do anyone else have thoughts on that question?
Yeah, I mean, I just kind of echo what Michelle said. It really depends what your goal is, especially for early signs of establishment with seedings. It can be pretty hard to figure out what's going on so that, it's the sophistication and the number like of tools that you might want to use, what kinds of tools really depends on your question. But there's some really like some of the stuff that Michelle presented on is really intuitive and easy for people to use to get at least a general sense.
Yeah, I think that's been huge in the success of some of the work in Oregon that they do. They adopted those relatively simplistic ecological state maps, but they have good foundations of and alignment with other more complicated strategies. And maybe that's a key takeaway is sometimes we don't need to have every single species dialed in for a lot of our management questions, but we're okay with being a little more generalized in our approaches.
Thank you so much. And then another question, what are the best methods, tools available for capacity limited managers to assess treatment effectiveness in the short and long term?
And that could be reworded as any manager. Chad, did you have thoughts on that? Oh, you're muted.
It obviously depends on the management question, right? But with the advent of daily imagery archives at high resolution, I think the the capacity just falls with how much field monitoring time they have. But I've been doing a lot of field campaigns where I can go collect data within a day if it's good and it's capturing the heterogeneity in space. You can get a usable product in a day, and it's not expensive. It's just you have to know the techniques and a solid question. So I don't think it's capacity limited. I don't think we should just push it off onto um, any product that's already available. Everything should be a little bit customized for the local environment in question.
Stella, I think you maybe were going to say
Oh,
something.
yeah. Awkwardly unmuted myself, so I guess I can say something. Yeah, I don't know. I think it's kind of the same answer that we already gave about some of those easier eco state kinds of methods and using your tablets and everything. And also maybe thinking about your monitoring before you put the treatment in. I think a lot of people have advocated for that. Usually makes it a lot easier if you have a plan for how you're going to monitor before you even install your treatments, would be a general thing. And that's maybe limited, but it might actually not take that much time to think about that. And sometimes that goes by the wayside. So that would be another recommendation.
Yeah, I think that's true. Go ahead, Michelle.
Yeah, I echo that pretty strongly with thinking about the ORMP data and the results we're, starting to have is, the treatments that were put in before we knew about this project. Those ones are the most challenging because we don't have pre-treatment data, and it's difficult in that particular landscape to find comparable controls because so much of that landscape is getting treated where these things are a problem that your controls aren't the best controls. Your pre-treatment controls are the best. So it gets a little tricky. I would also add that multiple lines of evidence is really important. And that's one of the pillars, I guess, of what we're trying to accomplish in ORMP is they don't do every one of their protocols everywhere, and they are using everything from satellite imagery to LPI spread across. So, they've got some LPI, lots of rapid plots. They're also using remote sensing. So just having multiple lines of evidence to try to make these decisions, and that helps spread the capacity need out a little bit across office, field work, that sort of thing.
Yeah. Well, and I think some of the changes that have been proposed in terms of land health standards, it may be that the program breadth with BLM, at least, that will be using monitoring protocols won't be as narrowly focused on one or maybe two programs. And so they might be able to cost share or collaborate on some of these efforts, which would be a benefit as well. I had a question for you, Michelle, on ORMP that I didn't get to earlier, but I know that that was originally focused on managers based in Oregon, and we talked about that simplified ecological state mapping, but are we seeing expansions of that? And is it modular to other types of either more detailed or similarly coarse state mapping?
Yeah, so the group that creates those threat-based ecostate maps, they've now created Sagebrush biome-wide versions of those maps. And the data that we've been collecting in ORMP has been helping to refine the thresholds that they apply to the RAP data to delineate the categories, because we have the same sort of decision tree happening on the ground that they're employing through the remote sensing. So there's been some improvement based on that aspect from the mapping. And then from actually using ORMP across the landscape, you might have noticed there was a Nevada Department of Wildlife icon on a lot of those slides. So NDOW is also using this infrastructure across lots of areas of Nevada as well. And our team has used it across areas in Montana, in Idaho for different projects too. And essentially any of the types of protocols that I mentioned in Rome are technically available in the menu, if you would, for like an ORP type monitoring style. It's all the same backend for both those projects, actually.
Great. And it looks like Janae dropped a question in the chat that was for you, Stella, but the question was, for the parameters that met your expectations, what effect size did you see? For example, effect of burning.
I'm digging into it now.
Okay. So we will have an answer back from the group on that. I have a broader question for each of you to consider and maybe answer as well. And I think everybody wants to, find these technology tools and satellites, remote sensing approaches that would simplify and bring greater efficiency to our rangeland monitoring. And I heard Chad, you said we should avoid using satellite imagery for threshold level decisions. And certainly you had some other caveats about that, but I'm interested in thoughts from each of you on what you might consider a practical use of satellite imagery that a land manager might be able to use with some confidence today in likely decisions they face. And alternatively, Chad, if you don't have one of those, what usable scales do you think exist for things like RCMAP and RAP? Where would you draw that scale line? So since I'm focusing on you on that last part, Chad, I'll let you go first.
Yeah, I didn't mean to say they shouldn't be used for threshold-based decision making, but it's using the correct tool at the correct scale. So maybe for RAP or RCMAP, you shouldn't be using those as absolute value threshold covers if you're going to choose to treat an area because it has, say, 20% cheatgrass cover. Like Matthew said, right? We have that false moderating effect towards the mean. But if that's going to be your threshold that you're going to determine that you want to treat with, then your monitoring data should be based around that threshold. And then you should have a unique spatial product derived for your site um, to answer that question.
No, that's good clarification. Thanks. I appreciate that. So for anyone else willing to put out that I would confidently make this decision with satellite imagery, that is out there. Matthew, you're jumping in. Go for it.
Oh, I have to weigh in on that. I mean, I'll echo the general sentiment that thresholds in general make me uneasy because there's error in the maps. And, if you're at 19% cover versus 21% cover, you might be on either side of the threshold, and you're still within the RMSE bounds of that component likely. And that might lead to, being placed on one side of the class or the other and making a decision based on that. So if we could get away from like a binary kind of threshold and sort of get more classes, like an in-between kind of class, like a definitely yes, maybe, and no class, I think that can be more helpful and
Yeah.
and more statistically justified. Now, in terms of what can be used right now, I mean, I think temporal trends uh, are really informative, and they definitely can remove some error in the products in individual years, especially when you're summarizing a trend over a large area. So, for example, you're seeing a net increase in sagebrush cover over some 10,000 acre allotment or something. That is more likely than not a real pattern. So the combination of time and space definitely add weight to that conclusion relative to looking at small areas or even individual pixels and individual years for that matter.
Yeah. So fuzzy thresholds, okay. And
Yeah.
then so Stella or Michelle, either of you?
Uh, I guess I may have lost track a little bit of the question with the threshold part. Um, but
Basically, yeah.
if you're asking about confidence in making decisions, is that sort of your
Yeah, I mean,
main
maybe you
question?
could think like at what scale do you think decisions using satellite imagery platforms we have currently are good bets?
Um, you know, like spatial scale or even temporal scale wise, I guess
Sure.
I feel like there's a lot of sort of effort that in the academic literature that's gotten into, oh, you should look at like a larger size areas. Oh, don't just look at one pixel, don't look at one year or, something like that. And then I feel like I see people using these products all the time at relatively fine scales. So and then maybe also just losing sight a little bit of that. I think Matthew had some interesting points about, the regression to the mean and then also just general error. So maybe we just need to be better about communicating that error and letting people think about it for themselves. So if you care if your treatment led to a decrease from 20% to 10% invasive annual grasses, and you're trying to look at a huge area, maybe you're going to be able to see that signal.
Hmm.
But if you're looking at a really small area, with some of our current products, maybe that's, not reasonable. And if you have the estimate of error very clearly in front of you while you're looking at these nice little decision tools that we have available, I think that might help people a lot. So
Mhm.
just presenting the error in these models more clearly, like right up front, almost like in your face, I think could be useful.
That's a good idea.
That's a non-answer though.
No, that's good. I think those are all good thoughts. I think our management partners also know that when they're planning things, they are probably getting on the ground and doing some even if it's just ocular verification of the information they have. But of course, that's always important too. Well, we've reached the end of our webinar time, and I want to remind everybody we have one more tomorrow that is on our fire theme. And with that, I'll hand it to Janae for some last wrapping thoughts.
Yeah, thank you all attendees for your participation, and thank you so much presenters for sharing your research. And we'll get the video. It'll take a little bit, so it'll be a couple weeks, but I'll email you. I'll reach back out when that's ready. And yeah, if you would please take our 3-question survey that will appear when you close out the webinar. That's very helpful for us. So thank you again, everyone. We really appreciate learning about all this great
Yep.
stuff.
Thank you, presenters and audience. Love having you here. We'll see you tomorrow.
Have a great
Thank you
day.
for organizing.
Yeah. Thanks for being here. Bye.